Now the merit, or one merit of Peter Hammer, was to have shown the following. Namely that quadratic which is a limitation, quadratic pseudo-Boolean functions, and only those which have all submodular terms, here's another restriction, they can be minimized exactly in polynomial time, so efficiently, using max flow or min cut on a graph that has been constructed in a special fashion. And I will explain this, what max flow min cut is, and then afterwards how the graph is constructed in the first place. Now, quadratic, we know what it is. What does submodular mean? So a submodular function, let's say psi on a set S, there are various definitions of submodularity, but one of them, they're equivalent. One of them reads as follows. So if I have psi of x and psi of y, this should be no less than the union of these plus psi of the intersections of these. That must hold for all members of the set. And I rewrite it for our case here, let's say for considering just two adjacent vertices, which is enough because the rest follows through an additivity theorem. So let's just look at a size, a set S of size 2, psi of 1, 0, psi of 0, 1, so if I have sets, the union can be written or can be obtained through a max operation, and the intersection can be obtained by a min operation. And if I really consider psi here as an interaction term between two adjacent random variables, it tells me that the energy for a label change, so if I have a transition from 1 to 0 or from 0 to 1, the sum of the energies associated with label changes must be no less than the sum of the energies associated with constant labels. So this is some kind of smoothness assumption, at least in our context. And if this holds, and if we're only looking at binary MRFs, then we can solve them exactly in only polynomial time rather than using an NP-hard algorithm such as integer linear programming. So that is a tremendously important result. So to do it, we need this max flow min-cut algorithm, which we will look at after the break.